We're back with a new laptop for some old code. I'm Ray Myers. Welcome to Craft vs. Cruft. Today we're going to go back to the International Obfuscated C Code contest, which we've done one refactoring challenge on before, which was about a Lisp interpreter. But this one was inspired by some obfuscated code that was from my first refactoring challenge that wasn't actually a part of this contest, which was the famous donut video, which is by far my most successful video, which prints an ASCII 3D donut, and the code itself is in the shape of a donut. I'll link it in the comments. I happened to get a comment on that recently. I love to see your comments on these videos. I try to respond to them all. Which is thank you for taking an interest in IOCCC, that's International Obfuscated C Code Contest. Speaking of rotated donuts and pretzels, 2005 Persano has a subtle bug we did not have time to investigate fully. How intriguing! A little bit of a breadcrumb trail he's dropping for me. So, Leo Braucus, this is in fact one of the judges of IOCCC, and I was not in contact with them before. So it is really great to hear from you, Leo. How could I not take the bait on this one? So let's go. Let's go all the way back to 2005 and take a look at Persano, which was the Best in Show winner that year, right? So first of all, this is the code. All right, we got some setup here, and then we've got this just weird shape of a mathematical notation. Looks like capital S raised to the third power, and then a short main method. So not much code here. The brilliant thing about all these IOCCC entries is they're all quite short and yet so incomprehensible and do often so much in that amount of time. If you go to the hint text in these, kind of like the README, it'll tell you a little bit about what it actually does. And it turns out that little bit of code generates an animated GIF of what's called a PQ Torus knot. And it talks a little bit about what that is. It's, a geometry thing. So over here in the wiki page, we can see examples of PQ Torus knots, right? So the 5-2 Torus knot looks like that guy. A 9-2 looks like that, and so on and so forth. So you're telling me that bit of code generates animated GIFs of these knots. Well, okay, I want to see that. So what I've done here is basically downloaded this code into a new project. We're going to be using C Lion for the most part, which is the JetBrains C editor. It's basically IntelliJ for C, because although its refactoring support isn't as good as the refactoring support they have in their Java IDE, it is better than most other things you're going to find for C. So as you can see, we've just got the code here exactly the same as it is online. We've got the hint pasted into the README. And then we've got just a little make file they provided, and then this CMake list that we need to make the IDE happy. So let's just take that and copy this, and I'm going to put this in a GitHub repo if you want to follow along. Link in the description. And I actually do encourage you, to download this file, play with it yourself, try to follow through some of these steps and learn how to apply some of these techniques on your own. We're going to do this time instead of doing like a multi-hour because the IOCCC entries, they're quite hairy. They take a long time. Let's try staging this into multiple parts. So I think in this first entry, we're going to get the code formatted. We're going to get some tests around it. We'll make some basic transformations and then save the rest for a later installment. So that said, let's make our initial commit here. Looks like we've got everything we need. Let's go ahead and throw the IDE metadata into our gitignore. And the only thing I didn't mention is I've just got a little preview script here that will allow us to quickly show an animated GIF just for the purposes of making the video. That's OS X specific, but you'd have something else you could use on your own platform if you wanted to. So, good. Yeah, I think that's good. I've got a Clang tidy file, which we'll talk about in a little bit. That's a linter. So, can we compile it? Yes, there's some warnings, but it can, in fact, compile. We got an executable, and looks like it wants P and Q arguments, and then some third argument, and then it will just output the contents of a file. Third argument's optional, so let's start out with give it 1 and 1, and output into 1 GIF. Now let's look at that. Well, how cool is that? That little bit of code, it can make a spinning 3D donut, just like we had in that previous entry, right? But we can do other shapes too. So let's go up to this wiki page, right? So let's try the 3 and 2 torus. So we'll do 3 and 2, save that to 32. Preview that. Wow. Okay, let me get that a little bigger so you can see it. Okay, and then we try getting even crazier with it. Let's try doing a 9-2. All right. So when I was little, I would actually look at these IOCCC entries, and I'd think, wow, I could never possibly understand, how this is doing what it says it's doing. And honestly, as a mature programmer with 15 years in the industry, still just looking at it, it looks just totally unfathomable. And it is like just by reading it and reading it and reading it and reading it, I would never be able to tell you what it does. And even if I knew C a little better, even if I knew trigonometry a little better, I would probably still not, just by looking at it, because the insight's been buried so much here. The only way we can attain any insight about this is incrementally, is by refactoring it step by step by step, finding a little bit of insight, embedding that in the code, finding a little bit more insight, embedding that in the code, and slowly untangling this knot, right? And that is a good way to do it on real code too. It's called read by refactoring is one of the ways you can call it. So what a lot of people try to do is they try to just like read code fully and understand it all before they can make any changes to it. But if you learn these same techniques, some of which we're going to use here, you learn how to obtain little tiny bits of insight and embed them in the code as you go in these little safe steps. So where do we start here? Well, there's one thing which we didn't do in the original donut video, which we did in the follow-up to it, which is put tests around this first thing. Even though we're going to make steps that should all themselves not change anything, it is easy to have some human error even doing these theoretically safe steps. So let's see if we can introduce some tests the first thing. The good thing is there's a plain input and output. You put in the numbers, out comes a GIF. So that means that even though this code isn't made for testability, you don't have small testable chunks within it, you can still go end to end and make, what are sometimes called approval tests, sometimes called golden file tests, pretty easily. So what would that look like? Well, I think we would basically generate a series of GIFs that we expect to come out from different inputs. Maybe we'll put those in a folder called golden. And then in a folder called out, we'll go what we actually got. And so what would this look like if we made just a little script to validate? Now I start all my bash scripts with this is what they call it, unofficial bash strict mode. So let's throw that at the top just before we do anything else. Among other things, it means that on the first error we will stop. So let's see if we've got Persano bin in the directory, let's say. And we want to generate Persano11 goes to out11.gif, right? And we can't run it yet because we haven't marked it executable. Let's do that. Okay. We got a GIF in there. So let's say we want an array of these test cases, right? So let's go. So let's make a function here, run case, something like that. And that will take a P, which will be the first arg to the function. It will take a Q, which will be the second arg to the function. And we'll pass P and Q in here. And P, Q into the name. And then let's just use the first few cases in Wikipedia, say. Run case 1, 1, 3, 2, 5, 2, 7, 2, 4, 3. So we're not testing anything yet. We're just generating cases, but we expect this to be the correct values, right? Because we haven't changed the code yet. So that means this is going to be our golden file. Let's see what some of these look like. Cool. There's 7.2. About 4.3. These are really cool. And by the way, the bug that the original comment happened to mention is called out in this hint.txt. 316 is the one that they're calling out here. So let's throw in 316 as a scenario so we can see what it looks like. All right, that's got a lot of lines in it. Let's blow this up here. Oh, you see? This bottom area like disappears briefly. Apparently they never figured out why that was. So there's one little Easter egg here, and there's actually a couple of others. Exercises for the reader. The surface is composed of many small polygons. Try to make it smoother by increasing the number of polygons. That's for 1 point. For 2 point, figure out how to change the radius of the tube cross section. So that would be, making this And then for 5 points, locate the famous transcendental constant pi in the code. Because, if you're drawing circles and things like it, you often need some value of pi. Apparently, they've used some strange way of computing it. So, great. Well, along the way, we'll see how many of those we can knock out. We'll see if we can find that bug. But for now, we've got that bug in our set of pre-existing cases. So if we change that example at all, then we should be able to find out. So let's move this output into our golden directory. So that is now, this is what we expect it to always be, and we can commit that with the repo. You try not to have too many big binary files in Git, but a few are fine now and then. So then we're going to generate these when we run our test cases again, but we're also going to diff the output with the equivalent in our golden directory. Point is, this should return an unsuccessful value if they differ, which, because we're in strict mode, will fail us out of the entire script. So let's see what we've got here. And we'll say what we're doing. We'll do an echo here. Okay, cool. Now, what if one of these were to be different? So let's, just for sake of argument, I'm going to copy 7.2 to the current directory to save it off. And then I'm going to copy golden 1.1 to golden 7.2. Basically make one of my test cases expect the wrong data, just to make sure that this is capable of failing. All right, they fail, and notice from my command line it is showing it returned a non-zero exit code. That's why my command line has this red indicator there, and that means if we ran this in a continuous integration server, that it would fail the job usually if that one script failed out. So this is behaving as a test script should, right? Stops right there, returns failure. So that's cool. So now if we put this back, or we found it, we put 7.2 back in golden, we've got a test suite that we should be able to use pretty well. And let's check out a refactoring directory so that when you go to the main branch on this Git repo, you're going to find the original exercise. You can play along at home, and then in the refactor directory, you're going to find all the progress. So we'll commit as we go here. So we've got tests, which means we can start to make changes, but how on earth can we even conceive of making any changes to this? Well, the first place to start, usually what I do when I'm attacking these IOCCC entries, they often use pretty heavy use of defined macros. As you can see here, the word for has been defined to X, and we've got this other situation where for loops, because this is an X loop, but really it's a for loop because of that, where there's a whole looping structure that's defined as in terms of a defined macro here. A formatter is not going to be able to make much sense of this code until we get these macros out of there. So start there and then do formatting is what I generally would do. So let's start, and often I have to do this in a text editor, but since we've got CLion now, it might be able to inline the macros pretty well, so that's kind of cool. That'll save us some time. In the obfuscated donut video, I'm in a text editor the whole time if you want to see some of these tricks without the use of these tools. So inline, 13 uses of 4 being the letter X. Yeah, let's definitely do that. And it couldn't do the one that was inside another macro. Okay, fine. So that just leaves us to do this one. And then let's grade this out because it's unused. Cool. Is that kosher? Are we still passing? Yes, we are. So let's now inline this for loop macro. All right. And then we've got one more macro, but this is really just like a constant. So just to avoid macros in general, I'm going to make it a constant, but that was really not hurting much anything. It wouldn't have thrown off the indentation or what have you. So great. Now, having done that, now that we don't have like X loops where 4 would do, maybe we're going to have a better luck formatting, but I'm not actually going to use the IDE formatting because these are, the indentation is so messed up that even JetBrains formatter tends not to do that good of a job. So I'm going to use the Clang formatter, which through trial and error I found tends to work a little better on these. So I'm going to run that and I'm going to output it to another file. And I'm just going to take that paste it in here. All right, cool. So still looking completely ridiculous, but at least there's some structure. And let's, although a formatter, should never break things, we're in extreme circumstances. So let's go ahead and build it and run it again. Cool. So let's commit there. Next, I'm seeing we've got some type defs. You notice we've type defed void. So that's probably also throwing off our ability to see what's going on, right? So can we inline that type def? Yes, we can. We've type defed int to be the letter underscore. That's completely ridiculous. Let's inline that. All right, let's see if we have any better luck. Let's run the test here. See if we have any better luck formatting it now. All right, starting to take shape. So format and eliminate defines. The next pass here, I'm noticing that we've got lots of loops that are on one line, but what they're doing on that one line is just a ridiculous amount of things, right? Here's a good example. Lots and lots of examples of this. And I think it would be a good step to just go through and put the optional braces in all of the blocks that we can. That should make this a lot more readable, allow us to break up those one lines without then disrupting the structure of the loop. And you notice that it says statements should not be inside braces because we've got a bunch of clang tidy rules, which is a static analyzer, a linter, and that is one of them. So through trial and error, I've found, ones that I think would be viable to check, and I've turned on as much as I can. You notice when it's got a minus sign at the beginning of it, that's like an exception, one that we don't want to include. So we want readability star, so most of the readability rules that Clang Tidy offers, but then not the one about identifier length, because that's just, we're not going to have a lot of luck getting every last identifier down. Similarly with magic numbers. And so there's a few exceptions, but generally we have a ton of warnings turned on to point out when anything funny is happening. And you can see those in the problems tab. So that you noticed when we compiled it, there were just a couple of warnings. Well, here's a ton of warnings in case we want that feedback. And we can actually get these down by a lot if we do some work later, I think. But for now, this is the one we're going to focus on. Let's put in the optional braces everywhere we can. We notice it's screwing up the indentation a little bit. No matter. We're going to run a formatter. We'll fix it. It'd be nice if we could do something that just like put this in everywhere at once. Let me know in the comments if there's a way to save some time doing it. I know on something like ESLint on Node.js, you can run a dat with -- fix, and it'll do all the fixes that it can automatically. Not sure if we can do that with C here. It's having trouble doing this one even so. Yeah, there it is. The ifs too, gonna do. All right, let's see if we've got any more of that particular type of warning. Yeah, I think we're good. So we'll go ahead and reformat. Now, cool, we at least see, some methods, some blocks, and so forth. But, this is still completely incomprehensible, right? So we're going to have to chip away at this for a little bit. Let's go ahead and test and commit what we've got so far. Add optional braces. So there's a number of major things going on here. One is that so there's a couple of major things going on here. One is that we've got all these single letter names that don't indicate what is what as far as the functions, as far as the variables in here at every level. So that makes it very difficult to know what's going on. We've also got this issue of code golfing where many actions and checks are being done within the course of one line. That makes it very difficult to follow what's going on. Another thing that's going on that's a little more subtle is that we've got all these global variables up here, right? So we've got P, Q, lowercase q, S, K, E, and so on and so forth. At what point do these change? At what point are they used? Any given block of code that we could be looking at, like where is it really getting its data and putting it? It's not just from its inputs, right? Potentially from all these globals. And so those are three factors that we're going to try to make some headway on. Looks like we've got some stray space before main. One that's easy to start with is to chip away at these global variables if we don't know where else to pull knowledge. So while that's somewhat arduous, I think chipping away at these global variables may be a a pretty useful endeavor for us, just so we can get a handle on what the flow of data is. We can see if it is obvious what any of these other things are doing, so we can start to squeeze some knowledge out of them, though. Looking at this, it looks like U is just an alias for put char. Might be able to inline that. Throw, well, I would throw a line break regex out of that, but I guess I can just find the usages since we're in an IDE. Okay, that's put char. Put char and put char. Cool. Oh, see how easy it is to make a mistake with these? U59. Okay, line 159. Looks like we missed a usage. Yep. Excellent. And notice we're assigning F to cosine and Y to sine. Well, that's also, you know, those could just reference sine and cosine directly. It would be a little more clear. Still don't really know what's going on with these, but better than nothing. So what, F was cosine? And what, capital Y was sine. Oh, this is an equation with P and Q and such. This is probably something that would make sense if we were thinking about the trigonometry as far as what's being calculated there. This R is clearly a type. Okay, it looks like we've cast a double to R. That's kind of useless. Should just be saying double where we say R then. That'll make this code a lot more readable. Alright, sign again. Alright, so if we got rid of all the uses of Y, just one more. Great. So a couple less variables up here in the global scope, right? One by one by one, we take them out. Now, it looks like V is meant to be a double of length 3, but this is the only usage of it. So does that mean I can just say a double of 3 for these three things? Get rid of that. Not quite. Okay. Not sure why not, but all right. We must be using V somewhere else here, and it just can't find it. Ah, there it is. Are we using V elsewhere? Nope, just those. Okay. I was thinking maybe we keep the type def and name it something good, but looks like there's not many uses of it, so fine. We may extract out another type once we figure out what's going on a little better. So what about this U type? There's just that one time. So this is the way that's used. It kind of makes me feel like I do need a type def. I'm not a total wizard with this. My C is pretty rusty. Let's see. Let's just call it 4, and then when it's used, we'll at least know what's going on. What about this J type def, which appears to be some kind of function pointer of double to double? I'm not seeing any references to that left. That was probably what the sine and cosine were doing. So let's try that. Oh. 131. What's going on? It's using X and all right. So we've got all these global variables, right? So let's start with these here because I recognize P and Q. At least those are our inputs. What would happen if we just made those no longer available? Right? Where do our compilation errors show up? Okay, so this function requires P and Q. It looks like they're traveling together, these P and Q. So we could, if we wanted to, extract a struct, that we could pass them around with. For now, let's just use P and Q. All right, so int P, int Q. Now, just saying, okay, G takes as those arguments P and Q, that's actually, not going to necessarily help us because something probably calls G, right? And it won't be able to pass them in. But, one step at a time, we're going to follow the errors, right? So main also cannot assign to them. That's true. That is totally fair. So let's see that it will need to declare them here, and then they'll only be in scope here. Well, then what? I'm using the comma operator, lots of gratuitous use of the comma operator here. Maybe we do a pass and just get rid of those. Cool, it's flagging us because we're not using it yet, but we are going to have to use it. Now, I'm not seeing red, but I bet if we try to build it, we will. Oh, interesting. We just have an extra warning, but I bet it won't actually. Yep. Because when we had that function G, right, we just altered its argument. So I expected there to be a compilation error right away. So how are we using this? Okay, it turns out we're actually passing it to this function called M. We're passing it to M. And then M is taking this third argument as a function argument and is calling it within this loop. Okay, that's interesting. How else is M called? Right, so M is called with K, and M is called with G, and M is called with E. Those are the three ways. So M, you call M, and you might be wanting to run G in a loop, or K in a loop, or E in a loop. And either way, it's going to run like some sort of similar loop. But that presents a problem for us when what we're trying to do is reduce the amount of global scope being handed around, because these other functions that are getting passed in are relying on that global scope. So how can we then, pass these functions in? Well, we could make them all take some superset of each other's arguments, I guess, and then M could pass them all in. But M, I don't know if this really is an amount of saving of duplication that really warrants passing around function pointers in C. So I'm actually tempted to say that this is what we need to extract out, and then let's just have 3 versions of M. So what would that look like? Right, let's see if it'll actually extract a method here. And we don't know really what D is at this point. That's okay. We will learn one step at a time. It's creating a alias for it up there. I'm not a fan of it doing that right now, or a type declaration, I should say. So yeah. So then let's just make versions of M for all the ways that it's called. What were those ways again? K, G, and E. Okay. And looks like we've got this I in here. Int I equals A star. We'll simplify it a little bit before we copy it. Cool. So what I'm going to do is I'm going to say there's an MG and an MK and an ME. None of these take that third function argument. This one calls K. This one calls G. This one calls E. It's actually upset that there's something called ME in another library somewhere. All right, cool. Let's just lowercase these then. I'll shut that up. I mean, we want names for all these. We want to know what these are doing, but we don't really know what these are yet. I guess we could say they are looping these other functions, but that's like about all we know at this point. Little by little, we unlock more knowledge. So that means we no longer are using M. We're using M loop K on this one. M loop G on this one. And M loop E on this one. What E is, we know we're looping it. So a little while since we've built. What's going on? All right, so now we have conflicting types for E. got a few issues here. 76, implicit definition. Oh, okay, that makes sense. So it's going to want these to be running after the things that they are referencing, because C cares in what order things are defined if they're not going to be all declared at the top, which, since we're going to do so much rearrangement, it's probably going to be more hassle if we do that. Put in loop G right above where it's needed. All right, now we get the example we were hoping we got a little while ago, where there's too few arguments in the function call, right? So you may not remember that, but we're getting P and Q out of the global scope. That is what we're trying to do right now, right? So cool. We need a P. We need a Q. That means M loop G is going to need a P and a Q. Who's calling it? Just one reference. A lot of the functions in here just have one reference. That's going to make things a little easier. At least there's one element of this making things easier. So this needs P and Q. Pass it in. So who's calling E? All right, M loop E. So we've got loops within loops is what we're learning here. Okay. Who calls M loop E? Because now they need to pass that in. All right, and now we are back to the bottom of the file. All right, so this is helpful for us to see kind of what the full call chain looks like, the flow of data. Now it's angry because the function's still being passed in. Yeah. Took that out, we put those two in. Nice. So remove P and Q from global scope. Now, little by little, so O, D, and Y. Now let's stick with the ints still. They've been simple so far. So how are we using this guy? What is that? C? Is that a G? I think it's a G. So there's just one read in this line, or at least, actually, no, there's a couple of reads and a write in that line. On 150, which is in what giant function? E. Okay. And again, okay. So then there's a write at the beginning of E. Well, that's interesting, because if we're just doing, if it's all in E and there's an assign at the beginning of E, it doesn't seem like this needs to be global at all. Like, it seems like you could just define it like that. Nice. All right, cool. While we're at it, looks like we've got lots of comma operators. Maybe we'll do a pass of just that. Maybe we'll start next time with that. So what have we got with this S global? In this O function, we're assigning to it and we're reading from it both. And again, strictly that's happening here. In what order do they happen though? That's important. So we're modifying. Yeah, it does seem like from call to call of this O, we are, using the value. But if O is the only one that needs it, we could use something a little less broadly scoped than a global variable. We use a static variable, which is still bad. Like, it would still be better to manage our flow of data into and out of this function in a more explicit way. But at least this isn't accessible by the entire program. So I maintain that's a little better. What else can we get out of the global scope? We've got this int k. And it's used within this loop here where it's just declared, or where it's just initialized and then incremented and so on. So it seems like within that whole block, it might as well be self-contained. And then it's sort of used again down here. Is it used in other places? Looks like in G, it is again initialized before it's used. And in K, it is initialized before it's used. Not in main, but then it's kind of isolated. So this is like the beginning of the program. So it's probably gonna be 0 at this point unless T is doing something with it. It looks like T isn't doing much but calling itself. That's a little weird in and of itself. So yeah, I think basically everywhere we're using K, it could be declared within that particular function. So let's do that. Okay. It's K. Yeah, is used down here too, or else I'd put it way into this loop. It's K. We'll just put this in the for loop like normal. And it's K. All right, cool. So now what do we got? We've got E, which starts oddly at 256. And in E, we pass lower E over 2 there. We're comparing, we're assigning from it, we're not modifying it. Now E is still 256. So far it might as well just be a constant. I'm seeing this being a constant all the time. So if we want a constant, like we gotta have a global constant. That's fine. That's not a problem. A global variable is a problem. Okay. Well, I'll leave that where it is. I'm happy with it. Okay, so then we've got some doubles, some arrays. But I think that's where we'll pick it up when we start back next time, is let's continue to whittle down the global scope and then look at what we've got left, look at how it's flowing, and then start pulling some names out of this, seeing if we can put names to some of the concepts that we're seeing. All right, so I'm going to do a final commit here. Thanks for joining us. When we're working with these obfuscated C code entries, it can take a lot of effort to pull any insight out of it. But remember, Lao Tzu did not say, with patience, the slightly to moderately tangled cord may be undone. He said, with patience, the most tangled cord may be undone. Or in this case, a Torus knot. Thank you.